So here's how I define the discriminator, and this is just one of many possible solutions to this task. The first thing I'm doing is saving my passed-in convdim parameter, because I know I'll need to reference this later. Then I'm defining 3 strided convolutional layers, using my conv helper function from above. Recall that this function takes in our usual convolutional layer parameters, with a default stride equal to 2 and padding equal to 1. It also has a batch norm parameter that defaults to true. And this defines whether or not we add a batch norm layer to the outputs of our strided convolutional layer. So here my first strided convolutional layer is seeing an image as input, and each image from the SVHN dataset and each generated image should have a depth of 3, one for each color channel RGB. And this is producing convdim number of filtered output images, in this case 32. You'll also note that I'm using a kernel size of 4, and in the case of the first layer, there is no batch norm layer applied to the outputs of this strided convolutional layer. So I set the parameter batch norm to false. As I create my second convolutional layer, conv2, I'm using my helper function again, just increasing the depth of these layers from convdim to convdim times 2. I'm setting a kernel size to 4 again, and without any additional parameters, I'm leaving the batch norm parameter to its default value, which is true. And I'm doing the same thing for my third convolutional layer, only increasing the depth by a factor of 2 once more. Let's talk a bit about the shape of the input image as it goes through these convolutional layers. It starts out as a 32 by 32 image, and after it goes through each of these strided convolutional layers, it will reduce in spatial size by a factor of 2. So it goes from 32 by 32 to 16 by 16, 8 by 8, and after the third convolutional layer, 4 by 4. Now if I look at my diagram, this is going to look like a 4 by 4 convolutional layer with a depth of convdim times 4, which is 128. At the end of these convolutional layers, I know I also need to smush these outputs and feed them to a final fully connected layer that will output just one value that indicates whether an input image is real or fake. And so here I'm creating a final fully connected layer, FC, that sees every single output value from the last convolutional layer. As I mentioned, at the end we have a 4 by 4 image and a depth of convdim times 4, so this is how many inputs this layer should see, and it produces one value as output. So all these layers complete my init function. Then to my forward function, I'll actually pass an input x through all these layers. So I'm passing x through my convolutional layers one at a time. And you'll also see that I'm applying a leaky ReLU activation function to each of these outputs with a negative slope value of 0.2. After going through these layers, I then have to flatten the output from the final convolutional layer, which I'm doing using out.view, -1, and then the number of flattened inputs I expect. And again, this is our 4 by 4 image times the depth of that last layer. Then I can feed this flattened output into my last fully connected layer and return that output. There's no activation function here, and so this should give me my discriminator logits. And I'll apply a sigmoid activation function later on when I calculate the loss between these logits and some target real or fake labels. Okay, great. So as long as you have a few convolutional layers and you're careful with how you've applied batch norm, this should be a complete classifier made of strided convolutional layers. And next, we can move on to defining the generator.